Hello everyone, myself Sahel. I've recently joined the University of Newcastle as a postdoctoral research associate to work with Dr. David Pontin. So today I'll be talking about a roadmap to decipher the solar wind transition from local to global scale. So here I should give the first a brief overview of the solar wind. So solar wind is a stream of high energetic charged particles that fills the entire heliosphere, escaping the solar gravity. So there are broadly two classification in the solar wind, in the fast and slow solar wind in terms of their escaping speed. So one is 750 kilometer per second and another is 400 kilometer per second. So solar wind is filling the whole heliosphere. Our Earth and other planets are also embedded on it, and it can affect the Earth's magnetic fields. So this is really interesting to understand their physics. So one of the open question in this field is what is the mass budget, or what features are contributing to the mass budget of the solar winds. So you see in this figure, this is a coronal image where this dark patches is known as coronal hole, where magnetic field lines are radially outwards, so flow can escape from this. And there are these closed field regions. So fast winds can escape from these coronal hole regions, and slow winds can originate from this boundary of the open field lines and closed field lines. So to understand and to decipher about this mass budget of the solar wind, one of the potential candidate to support the mass fluxes to the solar wind is called solar specules. So what are solar specules? So now if we zoom into this, just take a little patch of this coronal hole where the magnetic fields are radially outward. You see these jet-like features. They are spotting jet-like features everywhere in this coronal hole, and they are made of cold dense chromospheric and near transition region plasma, where temperature ranges in between 15,000 to 80,000 Kelvin, and they generally go through these ascending and descending motions in the vertical directions and follow the magnetic fields overall. One of the crucial feature of them is that they are really ubiquitous in nature, so you can find millions of them over the solar atmosphere at any phase of the solar cycle. So we are trying to build a model to understand these specules to finally understand the solar wind. So here are some of the details of our radiative MHD simulation using the pencil code. So we are doing this radiative MHD simulations under this LT approximation, local thermodynamic equilibrium. We are also solving these radiative transfers equations using this Rosland mean opacities. And in the energy equation, we are including this Spitzer heat conductivity and radiative losses. So this is the typical initial density and temperature profile solving the hydrostatic balance equations. So Z equals to 0 represent the visible photosphere. Below that, we have 5 megameter thick convection zone, which is like turbulent. And above the photosphere, it is 44 megameter of the solar atmosphere. So as we go above from the photosphere, the density falls rapidly, around 6 order of magnitude, and temperature increases and reaches to million Kelvin. As these are MHD simulations, so you are imposing some magnetic fields. So it is the vertical magnetic field of strength of 74 Gauss, which is consistent with the observations. So now here is the result from our simulation. So these are the jets like features, what we call them as specules. So these are mainly generated as a response to the solar global acoustic oscillations, which you heard about yesterday. They have the peak frequency around 3.3 millihertz. So what happens, these oscillations are acting as like a vibrating membrane. They're giving kicks to the upper atmospheres, and these kicks are actually propagating in the upper atmosphere. There is a strong density stratification. Therefore, they are steepening into the shocks, and shocks are accelerating this plasma. So if I now show you one animation, so this is like a synthetic intensity profile around 80,000 Kelvin plasma, and here it is like 0.6 million Kelvin plasma. So yeah, so here you see these are the jet structures. They are following this magnetic fields, overall magnetic fields, and they are really tall, like 5 to 20 megameter. So regarding the mechanism, what I talked about. So here it is like you have now it is I'm showing you the plasma acceleration here, and here it is the plasma velocity. You see the green patches; they are like positive acceleration and positive velocity, and this black contours are showing you the shock front regions where plasma is going through a strong compression. So you'll see these spicules are actually following this shock front regions basically. So these are like slow image, these shocks. So, and this is our convection zone. So basically this acoustic mode is actually generating this kind of jets. So now we tried to actually develop a simpler model where we don't have a turbulent convection zone. We just drive the system with a sinusoidal driver. And we also did some of the some tabletop experiments, which you'll probably probably you have seen some of this in as a slow-mo video in YouTube. So this is like a test case in the solar with the solar plasma, and this is a polymer solution which we are vibrating using a subwoofer speakers. So they are completely different system, plasma and fluid, but typically we find that there are some similarities in terms of their driving acceleration and the local gravity, the driving frequency and the lifetime of these jets, and non-dimensional number like Froude numbers, which corresponds to the which takes care of the importance of the gravity over the inertial term. So they are in the similar range. So if I now show you one animation, so here we have removed the convection zone, just driving the system with the sinusoidal wave, and here you see there are a lot of jet formation. So these polymer fluids are like viscoelastic fluid, non-Newtonian viscoelastic fluid. So if we try something with the like Newtonian fluid like water or glycerin, we don't see any jet formations. So I'll show you here, like without magnetic field, if we just drive the system sinusoidally, there are like lot of Kelvin-Helmholtz vortices. But with including this small amount of magnetic field, which suppresses this gauge instability and helps to get this uniform, coherent jet-like structures. In the case of the polymer, like here C equals to 0 means concentration of the polymer is 0. So basically it is water. You see lot of water splashes and droplet formations. And if we just include the little bit of the polymer, you see there are these coherent jet structures. So what is happening? These polymer chains are acting as like a spring. They can absorb some of the extra energy from the system, turbulent energy from the system, and this springs can suppress instability called plateau rally instability. Even they can back react because these are viscoelastic, so they can back react on the flow and can act as a secondary. You can think of like a magnetic field impression on this. So basically the role of anisotropy is really important to get these jets and these high amplitude oscillations which develop this nonlinearity in the system. So we have done many quantitative and statistical analysis on this. If you are interested, please look into this paper. And now we can look for some of the dynamical aspects of these jets. So this is one observation from the Hinode satellite, where these are the jets, and you see this arrow shows you where these jets are going through a bulk rotational motion. So probably here, and here it will be a larger one. You see this one is a spinning, going through the spinning motion. So we are trying to understand what is going here. So for this, we need 3D and 3D simulations. So here it is a one snapshot where we have the convection zone. This is the tau equals to 1 surface, optical depth equals to 1. This is the photosphere. And this yellow isocontours are showing you the synthetic intensity of the jets. And these are the streamlines. I'm coming to this in a moment. So if I just take a cut of this and show you the cross-sectional area, at the first glance, you see this looks like a warp sheet-like structures against the traditional thinking of this cylindrical jet-like structures. So that actually changes your cross-sectional area, and that can affect your mass fluxes or energy fluxes, which can propagate it through them. So if I now show you one animation, so this is one of the first result that motivates us, and this is a new result. So these patches are actually these blue patches are actually shock fronts, and again, like 2D simulation spicules are following that with a typical time period of 5 minutes, and you see these warp-like structures. So now if I just show you one line of sight integrated simulation, like image, like line of sight integrated image in this direction, it looks like this. It retains these spike-like structures because whenever you integrating it, whenever you have multiple folds of this plasma sheet, it is becoming this brighter and retaining these spike-like structures. So here I'm showing you different field of views where we find this, in this different field of views, we are getting the spinning motions of the, here it will be clear, the spinning motions of these jets, quite clear, and we are trying to understand what is happening here. So here we find that whenever these spicules are rotating, so there are these helical streamlines. Streamlines corresponds to the velocity field. So whenever they overlap with each other, these jets and helical streamlines, velocity streamlines, they are giving this rotational impression. So indirectly, we can think of like whenever we in observation we find this spinning of spicules, there are these swirls exist or vortex tubes exist. So we find at least two categories in which one of them where we find this with helical streamlines, we find also helical magnetic fields. Like here, you see the magnetic fields are also twisted. So they are like typical signatures of the torsional Alvan waves, which are generated from the turbulent granulation process. Magnetic fields are anchored, giving perturbation to the magnetic fields. And as a response, these torsional Alvan waves are propagating in the upper atmosphere. The second kind is like, it is not reported yet. We find this kind of structures. Swirls are helical, but streamlines are helical, but magnetic fields are not helical, these red arrows. And we find that baroclinic instability is actually generating this kind of swirls. So baroclinic instability is coming from the neighborhood of the spicules. Basically, spicules are generating this baroclinic instability, getting some gradients in the density and pressures, because at the neighborhood you expect a strong gradient. So this is a completely spicule driven swirl, and again swirl is actually back reacting on it. And this is just some plots of the Poynting flux and mass flux. And here I want to just emphasize that the importance of the coupling between spicule and swirl is playing a really important role to have this Poynting flux generation in the upper atmosphere. For the mass flux, we find this positive mass flux and negative mass flux repeatedly within like 5 minutes period. And we at the end we find that if we just take a time integral to integrate the time in integrate the mass flux in time, we see a positive mass flux that can attribute to the solar wind. And this is my current interest, where I'll look forward to not only the radially outward propagating magnetic fields or open magnetic fields, but we'll take care of some of the magnetic field structures like this. So this is an eclipse image where magnetic fields have this arcade-like field and complex structures. So we'll study these streamers and pseudo-streamer structures to decipher the origin of the slow solar wind, and we'll study the underlying magnetic reconnection process and we'll perform this 3D realistic image modeling in MPI-MR backcode in a grid, something like this. So here is my conclusion. So we talked about the generation mechanism, where we find these large amplitude oscillations, and anisotropy is sufficient to assemble the nonlinear development and can generate these jets. And in the 3D simulation, we find this drapery-like plasma, and there are at least two different source terms which can generate these swirls, and we see the importance of getting the coupling of these two things like spicules and swirls. Yeah, with this I'll stop here. Thank you.
Well, just a comment. I have a subwoofer in my office. If you want to do a simulation,
Great.
stuff, take to schools.
Yeah. Nice to hear that. Thank you.